The recording is on. Okay, so good morning to everybody. So, welcome you all to take part in this season 3 talk of the Gauge Gravity Seminar Series, which is an online seminar series. This is a third talk of the season 3. So, this seminar series is focused broadly on diverse topics in gauge and gravity theories. These are held roughly once a month, preferably on Wednesdays, but we are flexible. And we record these talks and we upload them on a CHEP YouTube channel. So there's some introduction for the audience, so some instructions. So they will be muted during the talk, but if they have some urgent questions, they can raise the hand or put it in the chat box. So today's speaker is Professor Jordan Cotler from Harvard. So he did his bachelor's in physics and mathematics from MIT, and thereafter he went for PhD in Stanford University and the Patrick Hayden. And after PhD, he joined as a junior fellow in Harvard, and he became a faculty recently in Harvard itself. So today he'll be talking to us about quantum mechanics of Hartle-Hawking state. So over to you, Jordan.
Well, thank you very much for the kind introduction, for giving me the opportunity to speak. So, I'm going to tell you about some work in the last year or so. Some of it has been in collaboration with Christian Jensen, so that's this paper up here, as well as a more recent paper from this January that I'll also speak about. So, first, let's talk a little bit about what is the Hartle-Hawking state. We're going to be concerned for purposes of this talk on de Sitter quantum gravity. Now, de Sitter is a very natural setting for quantum gravity, given that we ostensibly live in a universe with a positive cosmological constant. What we're going to study is a wave function of, or a candidate wave function, I should say, of the early universe that was proposed by Hartle and Hawking in the early 80s. And this is the no boundary wave function, in which we imagine the universe starts off from, in this case, a hemisphere, and then expands exponentially in Lorentzian time in a global in a de Sitter throat, specifically a Lorentzian de Sitter throat. And sometimes, even though it won't be important for purposes of this talk, we imagine that we consider the wave functions as sum over topologies. This is some cartoon that represents the higher topologies. But again, the purview of this talk is going to be the leading contribution to the no boundary wave function of the universe, which is sometimes referred to as the Hartle-Hawking state. So what do we mean by saying that this picture corresponds to a state? How do we compute this? Well, what we do, which I'll show you in a bit later, is we consider a path integral, specifically an Einstein gravity path integral coupled to matter, in which we integrate over all smooth geometries that smoothly cap off in the past and that terminate in a metric gamma in the far future. Now, what I have in mind here is that the universe has spatial cross sections corresponding to hyperspheres. So, for example, if we're in 3+1 dimensions, the spatial cross sections of the spacetime correspond to three spheres. So, therefore, the metric gamma at asymptotia corresponds to a metric on a large sphere, a large radius sphere at future infinity. And the way we think about this metric is that we can write the metric at asymptotia in a Pfefferman-Graham expansion in de Sitter space, where gamma ij is the leading component of the metric at large t, the leading spatial component of the metric at large t. So we can take the Hartle-Hawking state. I've put it in these double tets to just as a mnemonic to remember that these correspond to states in gravity, which will behave a little bit different than states in ordinary quantum field theory. That we can express the Hartle-Hawking state in a basis of gamma. In other words, think about the example of a particle in quantum mechanics, just say single particle quantum mechanics, where you take a wave function psi and you express it in the x basis and you write that as psi of x. Similarly, we can express the Hartle-Hawking wave function as psi of gamma, where gamma describes the metric at infinity. So that is to say that as we vary gamma, which is this metric on the three sphere, we get the probability amplitude that we go from a no boundary in the far past to the metric gamma at future asymptotia. So that's what the Hartle-Hawking wave function represents. And that's the picture that we should have in our heads when we do computations. I'll be a bit more precise about how do you actually compute this a little bit later on. One of the basic questions that we can ask about the Hartle-Hawking state is what are its correlation functions? What are its cosmological correlators? So what you can do is that you can insert operators in the far future, and then you can glue a bra onto the ket, and you can compute cosmological correlators, say in the presence of an inflaton. You can see the degree to which they agree with CMB fluctuations and structure formation and things that happen later on. And in fact, the Hartle-Hawking wave function is notable because for purposes of many predictions of cosmological correlators, but importantly not all, it actually agrees very beautifully with experiment. It has certain features that don't agree with experiment that I will mention, but it is interesting that it largely does agree with what we observe in the context of empirical cosmology. So what we're going to be attentive to in this talk is some more subtle quantum mechanical features of the Hartle-Hawking state. So instead of computing correlation functions, we're going to try to compute something more basic, namely the norm of the Hartle-Hawking state, that is, in which we insert no operators, no cosmological correlators. So this is the most basic object, and to give a preview of how it's going to work, when we glue the Hartle-Hawking state to itself, when we take the norm squared, we take the norm squared of psi hh, given here, and we need to integrate over all gamma, namely over all metrics in the far future. Now, the metrics in the far future have a gauge redundancy. They're only defined modulo diff times Weyl transformations. So uh, the natural gluing, or the natural measure, corresponds to integrating over gamma modulo diff times Weyl. And the question is, what does this equal? Now, this might seem like a trivial thing to do, because ordinarily we're not particularly concerned with the norms of wave functions in field theory. Usually it's the case that if we get a norm which is anything other than 1, then we just normalize the state accordingly. But we're going to see that something strange happens that has physical significance when we compute this. So first, it's useful to venture what answer we expect to find before we actually do the computation. So the natural answer that people for many years expected to find when you glue the ket to the bra, when you compute the norm of the Hartle-Hawking state, is that you might expect that the Lorentzian de Sitter throat here would cancel with the anti-Lorentzian de Sitter throat coming from the bra, and that you would get maybe the sphere partition function, that the hemisphere that prepares the state in the past would combine with this other hemisphere up here, and that would give you the sphere. Now, we'll see that this is true at tree level, but it's not obviously true at loop level. One reason why you might be concerned whether this is true at loop level is because we have an independent computation of the Euclidean sphere partition function in quantum gravity. It was originally computed at one loop by Polchinski, or at least certain features of it were computed to one loop. And famously, at one loop, if you're in d space-time dimensions, then the then the sphere partition function is proportional to e to the s naught, where s naught is the de Sitter entropy, times a factor of I, the imaginary number, to the d plus 2. So this I to the d plus 2 has long been mysterious, or rather its interpretation has been mysterious. It's related to the wrong sign conformal mode in Euclidean gravity, although that won't be the subject of this talk. But I want to point out that if you had guessed or stipulated that the norm of the Hartle-Hawking state was equal to the sphere partition function, you would be up for the rude awakening that there's these factors of I when you compute the sphere partition function, which are not very befitting of the norm of the state. We wouldn't expect that the norm of the state should contain negative numbers or imaginary numbers. That seems not so good at all. So what we're going to find is, in fact, that the norm of the Hartle-Hawking state does not equal the sphere partition function. So we do not run into this problem. but the answer that we do find is still strange indeed. The answer that we find, which is in this paper with Christian Jensen from last summer, is that we get an answer that looks in many ways like the sphere partition function, but without the factors of I, so I've schematically written an absolute value, but divided by the volume of SOD comma 1. And this SOD comma 1 is the isometry group of de Sitter. Or rather, if you like, it's the group generated by the conformal killing vectors on the sphere in the far future. Because this is a non-compact group, its volume is infinite, and thus if you divide a finite thing by an infinite thing, you get 0. So this suggests that at one loop level, that the Hartle-Hawking state is in fact a null state. And in fact, in follow-up work, I was able to show that it is equal to 0 to all loops in perturbation theory. So the conclusion, which we'll derive in the course of this talk, is that the Hartle-Hawking state is a null state at one loop. This also persists not just in the context of pure Einstein gravity in the path integral, but also when you couple to Bunch-Davies matter. That is, you can couple to matter, stable matter, importantly, you need it to have a stable potential so that you don't run into other issues, where you jointly prepare it in the no boundary state in tandem with the gravity degrees of freedom. In other words, you get the same conclusion that it's equal to 0 because you similarly get this division by this volume with SOD comma 1. So just one comment. This this volume of SOD comma 1 is not unfamiliar, and I'll mention a few calculations in which it arises or in which things like it arise. But the sphere partition function itself has in its denominator a volume of SOD plus 1, which is the group of generated by the killing vectors on the sphere. Now here we're finding an SOD comma 1, which is what is befitting for Lorentzian de Sitter. The difference, of course, is that SOD plus 1 is compact, so the division by it doesn't uh, kill the sphere partition function. But this volume of SOD comma 1, which we'll see is an important feature of Lorentzian, asymptotically Lorentzian de Sitter spacetimes, is going to lead to a null state for the norm of the Hartle-Hawking state. So this points to a important difference between the physics of inner products or pairings in Lorentzian versus Euclidean signature. That there is a fundamental difference between the residual gauge transformations, or in this case, natural associated isometries of the norm of the Hartle-Hawking state vis-a-vis the Euclidean sphere partition function. That these are just different objects. So let me tell you a bit about the inner product on asymptotic states. This was uh, originally studied in this nice paper from 2023 that Christian and I borrowed the inner product. But the argument again is very simple. If you have a wave function which is parametrized, or which if you express it rather in the basis of gamma, the basis of metrics at asymptotia, then when you integrate over the metrics gamma in order to compute the inner product, you have to account for the gauge redundancy, which in this case is a diff times vial redundancy. One other way of articulating this is that if you write a bracket of gamma, that when you integrate over gamma subject to this division by the gauge redundancy, this constitutes a resolution of the identity that we are inserting in between psi and ket psi and bra psi. So if you like, this integral arises from taking the psi bracket and inserting this resolution of the identity here. With this in mind, let us proceed to compute the norm of the Hartle-Hawking state to one loop, at first in pure Einstein gravity. We'll discuss then what happens when we couple to Bunch-Davies matter. That is, again, matter jointly in the no boundary state with the gravity degrees of freedom. So here's the expression again for the norm of the Hartle-Hawking state. It's a somewhat formal expression. But it will be useful for us to remind ourselves how we prepare the Hartle-Hawking state using the gravitational path integral. So let me expand that out. As I mentioned, the way that the Hartle-Hawking state is prepared corresponds to taking the Einstein gravity path integral. This is the Einstein-Hilbert action, where we integrate over bulk geometries with modulo bulk diffs. This is the bulk gauge redundancy. And we integrate over no boundary metrics, that is, metrics which smoothly cap off, which have in their far future a Lorentzian de Sitter asymptotic region with a metric gamma on the sphere cross section. So this is the object that prepares for us. This is the path integral expression that prepares for us the Hartle-Hawking wave functional. If we want to compute this object to one loop, it's natural to find a saddle point that we can expand around. So in fact, in the integration over gamma and g, there is, in fact, such a saddle point. It's related to the pictures that I was drawing before. In terms of gamma, in terms of the metric at asymptotia, the saddle point corresponds to gamma naught, which is the round metric on the d-1 sphere. So that is, the saddle point, at least in terms of gamma of this inner product, is going to come from a contribution in which the sphere cross sections are round spheres times some warp factor. And in fact, we can figure out what the metric g that this corresponds to if you take gamma naught, which is the metric at future asymptotia, and you bring it backwards in time, you find the corresponding bulk saddle to which it is attached. You end up with the Hartle-Hawking geometry shown here. So let me say a few words about the Hartle-Hawking geometry. So this is, as I said, the bulk metric that corresponds to gamma equals gamma naught. And here's one way to think about it. You suppose you write down the metric for global de Sitter space. So this metric, if you just take it at face value, corresponds to a bounce cosmology, which looks like a kind of Lorentzian hyperboloid. In other words, as t goes from 0 to infinity, it blows up, becomes the round sphere grows exponentially in the far future. But if you take t to minus infinity, it also grows in the far past. So it looks like it's really large in the far past. It shrinks to a finite size, it bounces, and then it becomes large again. However, the Hartle-Hawking state only contains, in a certain sense, part of that. So the future region, here shown in red, where t goes from 0 to infinity, looks like this exponential expansion. It looks exactly like this metric for t greater than 0. However, that for what we do is that we can think about this metric where we choose a complex contour for the time variable t. So this is the complex time plane where the x-axis is the real part of t and the y-axis is the imaginary part of t. Then this part of the contour from 0 to infinity corresponds to this exponential expansion. But for the Hartle-Hawking state, the saddle that caps off corresponds to taking the time contour and bringing it into the imaginary time plane to go up to I pi over 2. What this does, if you plug this into this formula, is that it corresponds to gluing the Lorentzian throat of de Sitter space to a Euclidean hemisphere. So if you do this continuation shown in blue on the metric shown here, that you will end up getting the metric for Euclidean hemisphere when your time contour goes into this part here. So if you like, then the Hartle-Hawking wave function or the Hartle-Hawking geometry corresponds to, I said, a Euclidean cap, which is smoothly glued onto Lorentzian throat. Okay. So then what we're going to do when we compute the norm of the Hartle-Hawking state is that we're going to expand around this geometry for the wave function and expand around fluctuations of this metric gamma equals gamma naught on the round sphere. So maybe
Jordan, I had a question.
yes.
It's just a simple thing. So this particular thing that you have written as a modulus, this thing, which is path integral from no boundary to the gamma. So,
Yeah.
is it like so the way you introduce the boundary conditions at that initial time, which is basically the no boundary time, and so does it is it sensitive to like how you are introducing the boundary condition? Like for example, it might be either Dirichlet, Neumann, or anything else, or something like that. So
Well, the idea is that there isn't really
it doesn't.
uh,
It seems like very sensitive to that.
well, the boundary condition at the future you could do in Dirichlet Neumann or your I mean you have different options for because that's a surface where you can put a boundary condition.
Yes.
But but the no boundary thing, there is no boundary. It's just that it smoothly caps off. There's no because it's a no boundary state, there is no place to put a boundary condition in the past of the kind that you said. There isn't a Dirichlet boundary condition in the past because there is no boundary.
So, for example, in this particular, usually like either way people impose basically either the Dirichlet, basically putting the scale factor to zero, or basically imposing the conjugate momentum, fixing a conjugate momentum to be some complex momentum in order to get a smooth rounding cap, basically.
Well, maybe you're imagining what the boundary conditions are. So one way you can think, sometimes people think about this is
Uh-huh.
kind of gluing a Euclidean cap to Lorentzian throat, and then you have to decide how you do the gluing at this cut.
Uh-huh.
And maybe that's related to what you have in mind. But there's a different point of view in which if you just consider this entire
Okay.
geometry, the
Okay.
only boundary of the geometry is in the far future. So
Yeah.
this is really just kind of this is just a kind of closed universe,
Yeah.
uh, which terminates into future asymptotic boundaries. So there's no, um, because it's closed off.
Mm-hmm.
Uh, there isn't something like a Dirichlet or Neumann boundary condition down here.
Mm-hmm. Okay. Okay. Okay.
Um,
Okay. Yeah. Yeah.
Okay, yeah. So anyway, um, so what we're going to do, oh, maybe my picture on the screen is obscuring this, but I'll tell you what the equation says behind it. If So what we're going to do when we do this integral over gamma is we're going to expand around gamma equals gamma naught, and then hiding behind here it's plus square root of g, because we're going to do a perturbation theory in root g, times h, where h is going to be the fluctuations around the round metric on the d minus one sphere. So here's what you do. We're going to consider one loop that we integrate up to gamma naught, which is the round metric, plus small fluctuations root g times h, where h is the metric fluctuations. So again, these are metric fluctuations at the metric at asymptotia. So here it is. This is psi Hartle-Hawking, where we're just looking at small fluctuations around the metric on the round sphere, which corresponds to fluctuations around the saddle. So I've just written this in our other notation, HH expressed in this basis of gammas, specifically in this case, gamma naught plus root g times h. One can compute this, and unsurprisingly, it has to be a Gaussian because it's a one loop wave function. So there's some one loop prefactor. There's a tree level contribution, which is the half of the de Sitter entropy. And then there's this Gaussian term here, where L is a shorthand for the hyperspherical harmonics on the d minus one sphere. So this is again just that we have some Gaussian. So let's talk about this Gaussian because it's going to have some important features. You see here, I've packaged the higher loop corrections into this order root G. Let me distill out, or let's just look at the Gaussian term, the part which is quadratic in the fluctuations h around the metric on the round sphere. So you see this h here is the same as this h. Can you see my cursor actually? I'm not sure if you can. Or
Yeah.
can you see
Yes,
the
I can see it. I
Yeah,
can.
good. Okay, great. So anyway, so these are the metric fluctuations, and this is the term, this is the Gaussian term here that we're writing over here. So you can write this actually in a pretty nice closed form. The form that it takes is some coefficient here, which has a positive real part. I call it c sub t. times essentially a metric, an integral rather, of the metric fluctuations against a kernel. And I've written the kernel in a slightly suggestive way. I've written it as a stress tensor two-point function. And in fact, what this kernel is here is literally the stress tensor two-point function of a CFT on a d minus one sphere. It takes precisely that form up to constants of proportionality. And you can essentially derive that the kernel has to take this form using word identities. So anyway, this is the answer essentially that you would expect in hindsight. All right, so this is the form of the wave function at one loop. And it has, let's focus for the moment on even d, even space-time dimensions for now, to avoid the complication of Weyl anomaly. Um, Focusing on d even is fine. Four dimensions is a good number, for example, since we notionally live there. So the simplest way of understanding this part of uh, the wave function is that, if you like, the result is that the late time de Sitter wave functions behave like CFT partition functions in d minus one dimensions, coupled to sources including a metric gamma. Of course, this is some like DSCFT logic, but this expression here that I've boxed has nothing to do with DSCFT. It's just that if you happen to like DSCFT, you'll be pleased that it should match your the aesthetics of your intuition. But the key structural features of this answer are twofold. The first is that it has no bosonic zero modes because of the fact that the stress tensor two-point function is on a sphere is positive definite. Moreover, it actually has no wrong sign modes. So let me emphasize this point because this is interesting and important. So often when we think about gravity, we are used to dealing with the fact that at least Euclidean Einstein gravity, in a certain sense, its Lorentzian counterpart, has a wrong sign mode associated with the conformal mode that we have to Wick rotate. So, we're used to having to deal with in the just in the Einstein gravity path integral, at least one wrong sign set of modes. However, in the wave function itself, the Hartle-Hawking wave function, which is a different object, it's not the Einstein-Hilbert action. It's a different object that is produced by the Einstein-Hilbert action, but is not itself the Einstein-Hilbert action. It's its own thing. This Hartle-Hawking wave function itself does not have wrong sign modes, and in fact, it is the kernel is positive definite. So that's important to keep in mind. This is like a perfectly great Gaussian wave function. You don't need to Wick rotate anything. You can integrate over the modes, and everything will work just fine. The second feature of the wave function is that it is SOD, comma 1 invariant. That makes sense for the reason that uh, this is a wave function corresponding to a saddle which possesses this SOD comma 1 symmetry. So of course the one loop wave function will inherit the symmetry of the background, or rather of the geometry that produces it. So so the fact that it's SOD comma 1 invariant is not surprising. So keep these facts in mind. It has no bosonic zero modes, and it has no wrong sign mode, so it's a good Gaussian. And also it possesses this SOD comma 1 invariance. These will be two key ingredients for computing the norm and for getting the conclusion that I mentioned.
So, Jordan, just the
Yeah.
previous slide. So this one loop thing that you're computing, so this is, I guess, is the path integral over this little h, basically. The
Yes.
fluctuation field. And
Well,
in
well
this
this
one,
is we're not integrating over little h. This is for fixed little h.
I see, I see. Okay.
Yeah. Next, we're going to integrate over little h, but we haven't done that yet. We only integrate over little h when we compute the one loop norm. Yeah, here this is at fixed h, and what I'm showing here is the h dependence that you get at fixed h.
Uh-huh. And in this one, basically, there are no, so as you go to the far infinities, there are no like IR issues you encounter because there are no zero modes you are seeing.
Yeah, I mean, of course, you do the usual thing where you look at normalized fields, you rescale
Yes.
your fields at asymptotia, but indeed, this is on a compact spatial slice.
Okay, okay, I see.
Yeah, I mean, well, so sometimes often, when people do inflationary cosmology, they work in a flat slicing in which the cross section is like Euclidean space as opposed to a sphere, and in that context, there can be certain kinds of IR issues, but we're not going to encounter those
Okay,
here.
okay, I see, I see. Okay.
Great.
Can I ask a question?
Oh,
In this
yeah.
expression, your CT is hiding the Newton constant, or is CT something not related to the Newton constant?
Yeah. It's hiding it's hiding the Newton's constant. It's yes.
So, but then you are writing the first line as 1 plus order square root of g. So, if I expand the exponential, then won't there be some mixing between the different orders?
Oh, sorry. So sorry. So there's a 1 over g that's in the tree level term. And then this is the one loop term. This is the one loop correction. So
Okay.
I spoke. So there's g's hiding in the tree level term. Maybe that's what you were asking.
Yeah. Okay.
Yeah. Okay. Good. Yeah. Thanks for your question. Okay. So how does the norm of the Hartle-Hawking computation work at one loop? So let me say it in words, and then I'll say it again a few different ways, so that let me sketch how it works, and then we'll reprocess it in a few different ways, so it makes more sense. All right. So the Hartle-Hawking state at one loop is a Gaussian um, over fluctuations of the metric at future infinity around the round sphere. That was the content of the previous slide. Now, the round sphere, um, yeah. So the round sphere, um, gamma equals gamma naught, is a stable saddle point of the one loop norm. Now, to integrate over fluctuations, we have to gauge fix the diff times Weyl symmetry via Faddeev-Popov, BRST, by, for example, gauge fixing the non-transverse traceless fluctuations of gamma to vanish. So that is, to gauge fix diff times Weyl, we have to impose some gauge fixing condition. So again, not a nice way to do this is that we can impose a transverse traceless gauge on gamma. Now, because of the fact that the wave function has no bosonic zero modes, the only other source of zero modes are ghost zero modes that can come from the residual diff times Weyl transformations that have not yet been fixed. So that is, when you do the BRST gauge fixing, what you find is that there are still some zero modes of the fermions that come from the gauge fixing, which correspond to residual gauge fixing that have not been fixed by a transverse traceless gauge. And these, unsurprisingly, correspond to the conformal killing vectors, specifically the SOD, 1 conformal isometries. But these same isometries or these same conformal killing vectors are also symmetries of the wave function. So what happens then is that you have fermion zero modes corresponding to these isometries, and you have no corresponding bosonic zero modes, or rather no corresponding bosonic modes with the right quantum numbers to soak them up. So upon fixing these residual gauge transformations, you end up getting a 1 over volume of SOD, 1. So let me say this again, because this is the key point. So your wave function is invariant under SOD, 1. When you do the gauge fixing of diff times Weyl, you find that there is a residual gauge symmetry under SOD, 1, which you then need to divide by, if you additionally gauge fix those modes. If you like, they correspond to fermion zero modes. But there are no corresponding bosonic zero modes to soak them up. So as such, the final answer ends up being proportional to 1 over the volume of the space generated by the conformal killing vectors, which in this case is SOD, 1. That is a group which is non-compact, has infinite volume, and thus you find that the norm is proportional to 1 over infinity, which gives 0. So specifically, this is the answer that you find if you're more careful about the dependence on S naught. This is the de Sitter entropy. You get some interesting factors here. You get this e to the S naught. And you get some one loop prefactor, but importantly, you get this division by the volume of SOD comma 1. So let's compare this answer to okay, so the conclusion is that the norm of the Hartle-Hawking state in pure gravity, pure Einstein gravity, is 0 to 1 loop. Let's compare this to the sphere partition function. Now we notice that the sphere partition function actually has some similarities, has the same S naught dependence, it has some one loop term, but one difference is that it has these factors of I to the d plus 2 noted by Polchinski, and instead of division by volume of SOD comma 1, as we found in the Hartle-Hawking interproduct, for the sphere partition function, we find a division by the volume of SOD plus 1. Okay. And this SOD plus 1 is compact. So it is interesting that these two answers look sort of similar, but they have some key differences. Again, the Hartle-Hawking doesn't have these weird factors of I because it has no wrong sign modes that you have to Wick rotate, and it also has a different group of isometries ultimately. So this factor of the volume of SOD plus 1 that happens in the sphere partition function computation arises by a similar mechanism as the one that I described in the norm of Hartle-Hawking. In 3D gravity, that is 2 plus 1 dimensions, one can actually show that this computation of the norm of Hartle-Hawking is one loop exact, namely that the norm is 0 to all loops. This is related to the fact that the only metric on the two sphere, mod diff times vial, is just the metric on the round sphere. So in a certain sense, you can gauge fix away all of the fluctuations. One useful point of reference, something that this might remind you of, is that in bosonic string theory, the bosonic string sphere partition function is proportional to 1 over the volume of PSL2C, which thus vanishes, 1 divided by infinity. It turns out that there's a kind of point of connection between this bosonic string calculation and the 3D version of the calculation of the norm of Hartle-Hawking. And this is not just an analogy, but there's a way of making this precise in various ways, which is discussed to some degree in these papers. So in any case, this boxed result here in blue is the main result, at least at a technical level. And let me elaborate on what happens at higher loops, and then we can discuss at the very end what it might mean. To understand what happens at higher loops, so your first reaction to this, or at least my first reaction to this was, okay, it vanishes at one loop, but what happens at higher loops? Is it non-zero at higher loops? The reason why you might wonder about this is that if the norm was anything finite, then we wouldn't really care about that because you can always normalize a state that's, if you have a state whose norm is equal to 57, you can just divide by 50 square root of 57 in the wave function, no problem. But if you have zero, if you have a null state, then okay, well that's real physics. You actually have a problem. You can't compute normalized correlators. So the fact that it's 0 at one loop, it suggests that we should figure out what's going on at higher loops to see if the fact that it's 0 continues to persist. And in fact, it does. Let's be a little bit more explicit about what happens with the one loop ghosts. So as usual, we expand gamma around gamma naught plus root g times h. And to fix gamma modulo diff times vial, we impose the transverse traceless gauge fixing conditions I alluded to before, but here let me write them out a bit more explicitly. So the transverse conditions on gamma ij can be that if you take its covariant derivative with respect to the round metric, you get 0. So with this index contraction, it's like a divergence. And the traceless condition is that if you take gamma ij and you take its trace with respect to the round metric gamma naught, then you get 0. So these are transverse traceless conditions. So when we say that these gauge fixing conditions have residual gauge transformations, let me say precisely what that means. What that means is that if you look at the variation of the gauge fixing conditions under diffeomorphisms and vial rescaling, so these are diffeomorphisms on the sphere, and these are vial rescalings of the sphere. And you compute this, you look at the order 1 contributions. There's contributions at order root g, but those are not important for the one loop gauge fixing. Those are important for the two loop gauge fixing, which we'll talk about, which I'll mention. But anyway, this is what you get for the variation at leading order. And um, to order one, you can simultaneously solve these variations of the gauge fixing conditions are zero if you let psi be a conformal killing vector and sigma to be its compensating Weyl rescaling. So this is the sense in which the residual gauge transformations correspond to conformal killing vectors. Now, interestingly, however, you might wonder what happens with the two loop contributions and the three loop and the four loop and so on and so forth, which are going to muddy the story. You're no longer going to have the conformal killing vectors correspond to the residual gauge transformations. But interestingly, something that I showed in a recent paper in January is that you can actually find simultaneous solutions to these equations to all orders in perturbation theory, to all orders in root G, to all loops, if you like. So it corresponds to a kind of interesting nonlinear or field-dependent deformation of the conformal killing vectors, which nonetheless satisfy the algebra of SOD comma 1. So it's some funny nonlinear some funny representation of SOD comma 1 that corresponds to deformations of the conformal killing vectors at higher loop level. So if we ask the question, is the norm of Hartle-Hawking equal to zero to all loops? The answer addressed by this recent paper is yes, in fact, it is zero to all loops. So I won't go into detail here about how to do this construction, but I'll point you to the paper. As I mentioned before, if you add in Bunch-Davies matter, again, that is matter, which we require to have a positive potential, so it's not unstable, that is then jointly prepared in the no boundary state. Well, adding the Bunch-Davies matter does not change the form of the result. Let me explain why one loop, although there's a more sophisticated argument to show that it persists to all loop order as well. Anyway, so if chi, for example, is the configuration of the matter field at future asymptotia, then at one loop, things are particularly simple because the wave function essentially factorizes into two. It factorizes into the one loop wave function for Hartle-Hawking, and the one loop Bunch-Davies wave function is a functional of chi. At higher loops, of course, they're going to get mixed up or entangled, actually. Okay, but you can show that this joint wave function is still SOD comma 1 invariant under the conformal killing vector transformations. And because of the fact that the one loop Bunch-Davies wave function has a finite norm, essentially the norm of the Hartle-Hawking state, by this I mean the joint Hartle-Hawking state between both matter and gravity. It factorizes at one loop into two pieces. One is just the norm of the Hartle-Hawking state in the absence of matter, and then the Bunch-Davies norm, which is finite. And by the previous arguments, this is zero. This contains this 1 over volume of SOD comma 1 factor, and therefore the whole thing is 0, 1 loop. Now, so this argument in a way which is explored in this paper from January also generalizes in some way to all loops in perturbation theory. So the norm of the Hartle-Hawking state, even in the presence of stable matter, is equal to zero at all loops. An important special case that you might want to study is the slow roll inflaton. Although I caution you that the slow roll inflaton does not have a stable potential. Sort of in the slow roll regime, you're kind of approximating the potential of the inflaton as being linear, which of course is not stable, but that's the whole point of inflation. Okay, so if we go to the slow roll regime, so here's particular parameterization of the slow roll parameters. Well, you get a similar looking formula. You can, so if here this curly phi corresponds to the configuration of the inflaton on some future cutoff slice, okay, well, you still get this factorization at one loop between the gravity wave function and the one loop inflaton wave function. And one comment is that because of the fact that the inflaton wave function has a linear potential, or that it contains a contribution which is linear in the zero mode of the inflaton at infinity. This is related to the fact that there's instability. Now, this reflects this weird fact about the Hartle-Hawking state in the presence of inflation, which is that this inflaton wave function is minimized when the uh, when the inflaton is low in its potential as possible, meaning that the Hartle-Hawking wave function predicts that you should have as few e-folds of inflation as possible, and therefore that space should have very high spatial curvature. Famously, our space does not have high spatial curvature, it's extremely low spatial curvature. And this tells us that the Hartle-Hawking wave function is not actually, at least in its naive interpretation, does not describe our universe for this reason. This was reviewed in a nice recent paper by Maldacena in the last year or so. So what's weird, however, is two-point
Jordan,
function.
can I clarify something? So, can one think of massive string modes as being these Bunch-Davies matter, or is this Bunch-Davies matter different from massive string modes?
Here I just mean something more banal. I'm just coupling a scalar with a linear potential. I mean, one could try to imagine this in a stringy context, but that's not what I mean here. I'm just doing the thing that a person doing cosmological perturbation theory would do. It's purely
Okay.
an EFT.
Just an ordinary scalar field in mind.
Yeah, scalar with a linear potential, massless scalar with a linear potential.
Oh,
Just the usual slow roll inflaton story.
yeah.
Now, anyway, the mystery I should just want to point out, just to finish the thought, is that okay, as I mentioned, the Hartle-Hawking state in the presence of an inflaton predicts not that many e-folds of inflation and also high spatial curvature, which of course disagrees with the experiment, but it also predicts Gaussian fluctuations of the curvature in the inflaton, which do really well agree with experiments. So it's this weird thing that, in a certain sense, the Hartle-Hawking state is great, except for this problem about the overall spatial curvature. So this is some thing that we don't understand about it. It's like a beautiful candidate for the initial wave function of the universe, but for this this weird feature that it predicts a high spatial curvature. In other words, the 2-point functions look fantastic and do agree with the experiment. Okay, so just one suggestive comment. I mean, one has to be careful in the context of the inflaton because, of course, this is, in slow roll, the naive inflaton wave function is not normalizable. You have to worry about how the you know how the inflationary potential levels out. But anyway, you might wonder if the fact that the Hartle-Hawking state has, in the presence of an inflaton, has this problem about the spatial curvature, if it happens to be a null state, maybe the problem goes away because maybe you're forced to, in a certain sense, consider contributions to the Hartle-Hawking wave function at higher topology, some of which do not have this problem. That's just a speculation. To give one other perspective on this result about the norm being zero, it's been popular recently and illuminating in various analyses to consider coupling a world line, or maybe more precisely, an observer to de Sitter space, and to understand what ensues. So we will consider this model of an observer due to a relatively recent paper by Witten, in which we we couple a world line that has some clock degrees of freedom. So we take this field, or rather this function q, to be positive. We take p to be on the real numbers. So the Hamiltonian of the observer is m plus q, and due to the positivity of q, this enforces that the energy of the observer is greater than or equal to m, which is like the rest mass, if you like. So this is a model of an observer that has a continuous density of states. So if you like, P is the time variable, and its non-compactness leads to a continuous uniform spectrum for Q. Okay, so this is just a model of an observer. So what you could do is you could couple the observer to the Hartle-Hawking wave function, or to the Hartle-Hawking geometry. And what happens when you do so is that that the natural saddle is one in which you have an observer here that goes along this world line. But then you have another contribution that wraps around the bottom, in which you have an anti-observer, if you like, or well, a kind of a second part of this world line observer. So this is the saddle that you get. Something that you might be familiar with if you're familiar with the analysis of Witten and others in global de Sitter, is that you have an observer in the static patch, and then you have an anti-observer in the anti-static patch. This is quite similar because these at the saddle, these two curves are at antipodal points on spatial slices. So you can glue the bra to the cat, and you end up getting an answer which is finite for the reason that the presence of the observer breaks the SOD comma 1 conformal killing vectors down to SOD minus 1 cross SOD, so SO1 comma 1. So in other words, when you put in an observer, you you break the boosts conformal killing vectors down to SO1 comma 1, which is just boosts along the world line. However, that's still non-compact, so you might think you'd run into a problem. But it turns out that there's a global time shift bosonic zero mode along the world line or the observer's world line, which cancels out this volume of SO1 comma 1 in the denominator. So the net effect of all of this, of putting in this observer with this clock degrees of freedom, is that you get a norm which is finite and in fact positive. It's good. It should be positive. It's the norm of a state. So this means an observer with a lot of entropy, by which I mean a continuous spectrum of total degrees of freedom, gives a finite inner product. So this suggests some connection to this paper by Chandrasekaran, Longo, Pennington, and Witten in 22, in which they analyze things in the context mostly of global de Sitter. Now, I don't know whether this coupling to an observer is deep or if it's a red herring. I'm inclined to think that in this particular calculation that I outlined, it's a red herring because usually when we do computations of cosmological correlators in cosmology, we have no need for an observer. When we do cosmological perturbation theory, you don't need to put in a world line with a clock. So the fact that I think you get a finite answer here is when you do put it in an observer with a large entropy is it's true, but I'm not sure that it alleviates the you know the fact that the Hartle-Hawking state has norm zero in the presence of ordinary matter fields. So as such, I present for you here this calculation about the observer, but I'm not exactly sure what it means or how seriously we should take it in terms of its interpretation. So let me end now with the discussion. So we've studied the quantum mechanics of the Hartle-Hawking state, the Hilbert space in which it lives, and its norm. And we've demonstrated that the norm is 0 to 1 loop, even with field theoretic matter, specifically matter with a stable potential. And moreover, this persists at all higher loops in perturbation theory. So in that sense, the norm of the Hartle-Hawking state is 0. It is a null state. Now, this presents a problem for cosmological correlators. Because if you compute cosmological correlators, namely you stick in a bunch of operator insertions, well, you ought to normalize that by the norm of the Hartle-Hawking state. Because the norm of the Hartle-Hawking state is 0, you do not have a way to normalize cosmological correlators. Moreover, I would say their quantum mechanical interpretation is not so clear for this reason. So this further brings into question the phenomenological relevance of the Hartle-Hawking state and what may replace it. And as I mentioned, in the context of inflation, which has its own subtleties about how they interface with this analysis, because the matter field is not the inflaton is in slow roll at least, we're taking a linear approximation of the potential, which is an unstable potential, but nonetheless. As I mentioned, that in the context of inflation, the Hartle-Hawking state has this problem that it predicts small number of v-folds and therefore large spatial curvature, which is not agreeing with experimental reality. So you might have a desire to kill the Hartle-Hawking state. And okay, well, maybe the mechanisms that I described here do so. And therefore, what that would mean, if that was true, although I don't want to commit to that interpretation, if that was the case, it doesn't mean that the no boundary state is 0 because the no boundary state is a sum over topologies. It would just tell you that the leading contribution to the no boundary state, which corresponds to the sphere cross-sectional topology, that one is a null state, and that you need to consider the subleading ones, which actually would then become leading. Let me conclude with a speculation. So one of the things that I emphasize in this talk is that the norm of the Hartle-Hawking state is not equal to the sphere partition function. Nonetheless, there is a kind of compelling pictorial image you might have in your head that if you glue the Hartle-Hawking state to itself, that you should get something like a sphere. So you might wonder whether there is a way in which you can have your cake and eat it too. One way to say this is that the norm of the Hartle-Hawking state is zero. But you might imagine that there is a different pairing. I've written it in the same notation, but I'm imagining it as a kind of Euclidean pairing as opposed to a Lorentzian pairing between the Hartle-Hawking and its time. Its so K is a complex conjugation operator. So here, what I mean by this is gluing a ket to a ket according to some Euclidean pairing. And you might wonder if you do a ket and ket of some kind with some Euclidean pairing, if you indeed get the Polchinski answer for the sphere. And if relatedly you glue a bra to a bra with a different kind of pairing, you get the complex conjugate of the Polchinski answer for the sphere. So that is to say, what I'm suggesting is that when you compute the norm of the Hartle-Hawking, you need to do a Lorentzian inner product. But there might be an alternative pairing, which is more like a Euclidean pairing, that is not the one relevant for the inner product of the Hartle-Hawking state, but would be the right kind of gluing to get the sphere partition function and its strange features and factors of I. So this is something that we're currently investigating. So, having left you with more questions than answers, let me thank you so much for your attention. Happy to take any further questions.
Oh, that was wonderful talk by Jordan. It was extremely amazing. So now the panel is open for the questions, so audience can ask.
So I have a question. Can I ask?
Yes.
Please.
So that one loop prefactor that you defined, that essentially contains all the contribution from TT modes, right? Transverse stresses modes.
Uh-huh.
Now there is always a growing mode, always in even close slicing. That modes that doesn't go to zero in the asymptotic limit. Like there are two modes, like one vanishes the asymptotic modes and one doesn't vanish at the asymptotic modes. So then why do you expect that one loop prefactor give you finite contributions? Can you elaborate that?
Well, there's a few different things you could be talking about, but one thing that you have to do, so okay, so the modes that cause it to vanish from the
Yeah.
BRST. So I don't think those are the ones
Yeah.
you're talking about. I think you're worried about the wave function. Is that right?
Exactly.
Okay,
There
good.
are two modes, right?
Yeah. So the key is that you have to right. So you want the modes that give you the wave function are modes that satisfy the asymptotically de Sitter boundary conditions and that are not pure gauge. So you can find examples of modes that have the wrong growth that don't satisfy the boundary conditions, which just don't contribute to the problem when you solve for fluctuations around the saddle. You can find other modes that look weird, but they're pure gauge, so you don't integrate over them.
So you are saying those modes that doesn't vanish at asymptotia, those are pure gauge modes. So you shouldn't take those modes
They
in
don't.
computing.
Sorry. So you're concerned about modes that don't vanish at asymptotia.
Exactly.
Uh-huh.
So
So
because
well, it depends exactly how far they're growing at asymptotia, but the modes that don't vanish at asymptotia, depending on what you mean by that, are exactly the ones that tell you the form of the wave function. Because if you had modes that died at asymptotia, it wouldn't give you, how do I say? It's that there's the when I'm writing the wave function uh, at future infinity, I'm looking at renormalized, it's like in holographic, sorry. It's like when you do the extrapolate dictionary, ADS-CFT, you have to renormalize the fields.
okay.
So there really are modes that, of course, survive all the way up to infinity, but those are the ones that describe what the wave function is.
So you don't take those modes like in computing determinant. So that's
Well,
in
you
small
do,
loop.
you do. It depends which ones you mean, but you have to worry about how fast they grow.
Okay.
I'm saying there's modes that grow just the right amount that once you renormalize them by the appropriate scaling dimension, then you get the renormalized fields in infinity. Other ones die too quickly.
I see. Okay. So then you get finite that one loop prefactor.
Oh yeah, you mean the one? Yes. You can compute the one loop prefactor. Yeah, so you're worried about the one loop prefactor that I called Z1
Uh-huh.
loop, is that right?
Exactly, Z1,
Yeah,
yeah.
yeah, yeah. So you can compute that. So that's a finite number in zeta reg, for example.
Oh, okay,
And
okay.
so we can compute it. Well, we're working on a
I
paper, and
understand,
so
okay.
in 3D you can compute it, for example. In 4D you can do it too, but it's a little harder.
Okay, yeah. Thanks.
Sure.
So, any further questions?
You introduce this nomenclature called an observer. So what is this observer observing? Is he making any measurements?
No, I mean it's just basically yeah. So there's words about observer and so on, but what I really mean is a world line with a clock. There's no entity making any measurements. It's just a world line with some internal degrees of freedom. That's all. But again, I'm not sure how seriously to take this calculate. So the calculation is correct that I presented to you, but the interpretation I think is just that, if you have enough stuff in your space-time, you're going to break the non-compact parts of SOD comma 1. So fine, you can put in stuff which does that. But of course, when we do things like inflationary cosmology, we don't usually put in like world lines with, clocks or something. We couple it to fields, and for which finding an observer or a clock or whatever you want to call it, it would be a very non-perturbative effect. So in
Exactly, yeah.
perturbation theory, when we do cosmological perturbation theory, my view is that we should worry about the setting of, fluctuations around saddles of fields coupled to gravity. And in that setting, that's where you get, that's where you get this zero. So you can get the zero to go away, by putting weird stuff in the space time. But okay, you can do it, but I'm not. That's not the thing we usually do in cosmological EFT. So I I'm ambivalent about it.
So, but if I'm supposed to think about it as a mental picture is somebody sitting there doing nothing, why does that entity creates a big entropy?
Oh, that's just the answer. All I mean is just that it's the clock just has a continuous spectrum of the clock degrees of freedom basically is a Hamiltonian that on the half line, which just has a continuous density of states. That's all I meant.
Ah, I see. Okay.
So, are there any further questions from the audience? So, if not, let's thank the speaker again for the wonderful talk. And so, sorry, Jordan, we basically was a little late for you,
Oh, it's
but
okay. Yeah, thanks for
yeah,
having me.
extremely wonderful talk. And maybe this is yeah, I mean, we'll be uploading the talk in the CHEP YouTube channel after the edits, basically. And then, so if you have any further questions, the audience can reach out to the speaker or just write to him and can just initiate some discussions or the further on. So thank you, Jordan, very much.
Thanks. Take care.
Yeah, bye.